Hi, this is Graham Bell. Welcome to the webinar, Ensuring Robust RTL Sign-Off with Stratix, FPGA, and SoC Design. Our first speaker will be Rama Venkata, Software Product Marketing Manager. Rama has 15 years experience at Altera. Altera is now part of the Intel Programmable Solutions Group. He's also held roles in IC design and serial IP product marketing in Altera. Previously, he's had over 5 years' experience in FPGA product planning and business development with other companies. He has an MSEE from the University of Southern California. Rama will begin his talk by bringing us up to date on the Cortex Prime software and how it is the current generation of software from Altera, now part of Intel.
This was named as Quartus 2 before. Now we changed the name a few months ago, and I will tell you why we changed the name. So Quartus Prime is, for those who are new to FPGAs or haven't used FPGAs, Altera FPGAs, this is a single tool that you can use to design FPGAs for Altera. So this has been the #1 design software in the industry in performance and productivity, and it's a complete package that you can use to design CPLDs or FPGA applications. So the goal of such a tool, obviously, is to make sure that you go to market faster, as fast as possible. It's meant to be easy to use, so we have very easy to use GUIs, graphical user interfaces, and we always partner with other industry leaders in whether it's Real Intent or any other EDA partner. We make sure that we offer the best-in-class solution together. So one thing to remember is that this is the easiest path from idea to reality, and that's what we call Quartus Prime. So what I want to point out is that we have had a history of innovation in the case of Altera. So for nearly 15 years we have been innovating, but I just want to point out some key innovations. Currently we are of course in 2016, but going back, we were the first ones to introduce the Design Space Explorer. So this tool lets you find the best setting amongst several hundreds of settings. So in FPGA design flow, you can have hundreds of different settings that will make your design run faster, lower power, etc. And finding each one of these settings can be a complicated task. So this tool lets you sweep the settings and find the best one for your design. But this also means that you will need several back-end computers to run this sweep. So moving forwards, we were the first ones, for example, to introduce SDC support, which is a synopsis design constraint, and the first STA-like tool for timing analysis. And of course, multiprocessor support. You might wonder what multiprocessor support is. This is meant to speed up your compiles. So FPGAs can run, for example, 1 million LEs. You can compile it in 4 hours right now. And the reason is we have multiprocessor support. Quartus will make use of every processor core that's offered to it on your laptop or workstation. So moving forwards, we have a DSP builder, which lets you implement DSP designs really fast from algorithm and models all the way to RTL. A system console is something that you can use to read and write registers, configuration registers, inside the FPGA to rapidly debug your design. QSYS is something that's very interesting, and going forward it will get more important because as your design moves up the abstraction level, QSYS lets you hook up different IPs like your processor to memory controllers, and it does this within minutes. So I encourage you, if you haven't used QSys, to use that. It will introduce registered blocks appropriately between the different IP blocks, but it does all of this in a very transparent way, so you can create a design really fast. Now, OpenCL, we were the first ones to offer OpenCL, which is basically a tool for software designers. So finally, moving forwards to the current day, which is SpectraQ. I will get to what SpectraQ is, and we are very excited about that. And SpectraQ is the engine that will power Quartus Prime going forwards for the next 3 years, even for the next decade. So moving on, you might have heard of Quartus 2, and Quartus 2 was in existence, or the name was in existence until, let's say, November of last year. And it used to support 40 nanometer in prior devices, including 28 nanometer. But in the end of last year, because of this new SpectraQ engine, and we had to convey the message that we have a very powerful new tool, and thus we changed the name to Quartus Prime. And Quartus Prime does support all the older families, of course, and it also supports the new 20 nanometer, the 14 nanometer, and of course going forwards into 10 nanometer. And on the y-axis here, you see the FPGA performance increasing. You see a big jump from 20 to 14, and this is because of our Stratix 10 families, which has a brand new architecture. I won't go into that architecture today because that's beyond the scope, but I encourage you to go to our websites and look at what Stratix 10 can offer. So Altera Design Flow, once again, for those who may not have used Altera devices, it's not that radical, and of course you want the same kind of design flow. It's like when you're buying a new car, you don't want the steering wheel on the roof of the car. So when what you see is quite obvious, you create your project, you synthesize, and then you do the technology mapping. This is just actually one step. Then you place and route your design, and of course in an FPGA, the routing elements are already pre-placed. You just configure the routing elements. Then you perform timing analysis using basically SDC-like constraints. Then you generate the programming file to program the FPGA. On the right-hand side, there's a more detailed view, and you can see on the top, sorry about the font, it's kind of small, but you see that we can write designs in System Verilog. You can use Verilog HDL or VHDL, and something called AHDL, which is an old language, and also you can do schematic entry. So we have a very wide spectrum of design entry methods. And of course, I don't show OpenCL here or high-level synthesis, but of course, that's also part of our plan. And you can, of course, simulate at this point. You can do functional simulation. Then you can move on to gate-level simulation once you have synthesized the design. And we offer something called Altera Model Sim, which has the same engine as the Model Sim Professional Edition offered by Mentor Graphics. And formal verification is something that we don't support right now. We stopped offering that after 40 nanometer. 40 nanometer and prior devices do have formal verification support. So this is quite obvious, and we want to keep it that way to keep the flow familiar to ASIC designers or FPGA designers and different industry participants. So moving on to what Quartus Prime really is, you can see that Quartus Prime now has 3 editions. For those of you who are familiar with Altera, you might see now that, hey, there's 3 columns here. The light edition was previously called Web Edition. The Standard Edition was called Subscription, and the Pro Edition didn't exist. So Pro Edition is something new, and this is the edition that will kind of evolve and grow in the future. And Pro Edition has SpectraQ engine underneath it. So you see the bottom 3 rows, which is kind of more dedicated to the Pro Edition. Some components of the SpectraQ engine is also present in the Standard Edition. So I do have a tick mark here, but it's a limited support for SpectraQ. So one thing I want to point out is a tool called Blueprint, which is very powerful for I/O placement and transceiver placement, etc. It will also do some clock and logic planning in the editions to come, and you will see a lot of exciting features coming into the Blueprint platform designer. So there's more to come. This is just the 15.1 edition, and there will be more features coming forwards. So the actual silicon itself, I show the current generation here, and we first rolled out the ARIA 10 families, which is our kind of a mid-range offering. And SoC refers to system on a chip, but what it really means also is that we have hard processors. We have the ARM quad-core processor in there. So MaxTen is our non-volatile kind of CPLD. So this is being offered in 55 nanometer flash. So this is its own configuration structures in there, so you can store configuration data. That's why we call it non-volatile. Stratix 10 is our next generation high-end FPGA with the tri-gate, also known as FinFET in the industry. And this has several architectural innovations. And the capability, once again on the y-axis, it increases as you go up these devices from MaxTen to ARIA 10 to Stratix 10. So now I'm going to go a little bit closer to what the topic of this webinar is. You will see here that FPGAs have evolved. On the bottom, you see these 3 graphics. In the 90s, we had introduced RAM at that time. I had just come out of school, and we just had RAMs, and PLLs were just coming on board 20 years ago. And logic sizes were exploding because of the dot-com boom, and at that time we had FPGAs going into several applications. FPGAs were moving away from just glue logic to kind of system-centric. It was playing a more central role in the systems. And then we came up with the DSP blocks, transceivers, PLLs, and hardened external memory interfaces. These are the blue blocks in this picture. And now in the current generation, or in the next 5 years or this decade, we will have more exciting stuff. We have floating point DSP, we have the hard ARM processors, and logic densities are exploding. We have 5 million logic elements, and generally this is interpreted as anywhere from 60 million ASIC gates to 70 million, which is probably like 10 ASIC gates per logic element. So and DSP performance, 10 teraflops. So the number of serial protocols have exploded. There's 50 plus serial protocols. Now, what does this mean to you? Going forwards, you may see hundreds of clock domains. Some of our customers already see hundreds of clock domains. Every channel can send its own recovered clock to the fabric. And again, there's also another angle to this. Our user base is getting broader. You have your low-end glue logic, and at the very high end, you have acceleration from the big guys like Microsoft. So we have to cater to this wide a range of customers. So we will end up getting a diverse set of RTL. So both of these are kind of where Realiton helps us out. And you will see that in this slide, sorry. sorry, hold on. I'm just going to quickly, just give me a second. Let's see. Hopefully you can still see my screen, but
yeah, we can see your screen, Rama. And
you can see my screen, okay? Because I'm getting a message saying it's paused. So do you see the slide showing a unified high-level design compiler?
no.
Okay. Okay, it should be okay now. So what I was trying to say was we have different front ends and different design entry methods because of a wide spectrum of designers. On the right-hand side in this slide, you have the hardware designer. These guys are just RTL guys. You know, they are very picky about clocks and setup time and hold time. So they basically are the original hardware designers that still form a wide, still form the bulk of our customers. But we, hold on. So now you have the embedded designers who are kind of like using DSP kind of modeling. So they use something called the advanced design block set and synthesize designs for FPGAs. There are the software designers who just write in C or C++, or even at a more abstract level, they have no idea about the hardware that they're even building into. They are like they think they're programming for Xeon, for example. So you get a wide spectrum of designers, and the RTL that comes out of this can become quite messy. So you need a proper linting tool. That's my point. You need very robust linting tools, and you also need to take care of your clock domains. So with that, I move on to the kind of the real intent portion. But before that, if you have any questions, I would be happy to answer.
This is an opportunity for the audience to go to the questions area on their control panel and type in a question. I apologize that we lost the last slide there on Rama's presentation. So I'll let you give you another 10 or 20 seconds to enter a question. If there are no questions, then I would like to run a couple of polls for our audience. And our first question that I'd like to run is, how many clock domains did you use in a recent design? And please select one and enter your answer. All right, we have over 2/3 have voted, and I see the voting has slowed down. So I think what I'll do is I'll close this poll. It says roughly 60% have 1 to 5 clocks, 15% have 10 to 20 clocks, and 23% have 20 to 50 clocks in their design. And I'd like to ask one other question, and that is, are you using any clock domain crossing verification software? That's to handle asynchronous clocks between different IPs and making sure your signal crossing is correct. All right, I think the voting has come to a close. Currently, according to our poll, 3/4 are not using clock domain crossing software currently, and 25% are. So that's an interesting statistic as we proceed to our second part of our presentation. So now I'm going to make Ramesh Dewangan our presenter. As Ramesh's presentation is coming online, let me introduce him. Ramesh Dewangan is Vice President of Product Strategy at Real Intent. He has over 25 years experience in engineering, customer management, product management, and marketing. Prior to Real Intent, he led the product marketing for the core product suite for RTL design at Atrenta, which was acquired by Synopsys. Began his career at Texas Instruments. He also, as I mentioned, also as a part of his career, he worked at Synopsys related to the Semitech Fund, also at Cadence and Terra Design, where he managed products related to formal verification, physical design, and timing analysis. He has an MBA from the Walter Haas School of Business at University of California, located at the Berkeley campus. And he has a Bachelor of Technology degree in electronics from the National Institute of Technology from Karnataka, India. It's all yours, Ramesh.
Thank you very much, Graham, and thanks, Rama, for a very good presentation from Altera side. I'm very happy to extend it to the solutions that Real Intent provides for Altera FPGAs-based designs. So as Rama mentioned, that getting the RTL right for FPGA is very important, given the complexity of FPGAs, which have many, many more clock domains than in the past, and RTL coming from diverse sources, including high-level synthesis. The RTL is extremely important to be clean before you start your implementation. And getting the RTL right for FPGA has got three aspects. First is RTL must be lint clean. What that means is RTL needs to be simulatable, needs to be synthesizable. There should be coding guidelines that have been followed in RTL. That is what a linter does, and Real Intent provides an Ascent lint tool for Altera FPGAs to have a very clean RTL. Second aspect of getting RTL right is functional integrity. There are a lot of aspects in RTL which may not function properly, and that you will find only after you have done your simulation. But there are several issues you can find early on using certification, using formal techniques, like whether your finite state machines are working properly, or if you have any bus contention, or if signals are toggling right. So those things will contribute to a functional integrity of the RTL. And lastly, the clock and reset domain crossing issues, which can be chip killers in your design. And that includes metastability, reconvergence, and loss of correlation issues. Other aspect of the solution is the static verification. Traditionally, the RTL design has been verified using dynamic verification, that is simulation. But simulation has its limitation. So the static verification, which includes both the structural analysis as well as the formal analysis, have become a very, very critical component of a viable solution today. And why? Is because static verification does not require any test benches. It is exhaustive. It also requires much less setup than a simulation requires. Also, it provides early detection. Even before you start your simulation, you can have static verification, get your RTL right for simulation. Simulation also has some limitation in terms of interpretation of X propagation. This results in what we call X optimism problem or X pessimism problem. They are verified using static verification solution. And overall, static verification results in shorter debug cycle time. So the idea is that if you are moving at the rapid pace with dynamic verification, static verification, you can put a booster on your verification cycle and close the gap faster. So Real Intent provides static verification solution for lint, for RTL functional, we call autoformal, and clock domain crossing. The idea of Ascent Lint is it takes raw RTL as input and provides you the feedback for getting the RTL compliant for synthesizability, for simulation, and also for coding guidelines. Ascent Lint is the fastest linter out in the market, and it is out of box, ready to go kind of linter. People have been able to get the first results out of Ascent Lint in a matter of minutes. Ascent IIV Autoformal adds sequential formal analysis to RTL. It's a deep formal analysis using advanced techniques, and it provides some of those functional integrity related issues in RTL in a very precise way. It has a unique feature called root cause analysis, which I'm going to cover later. Meridian CDC, the clock domain crossing verification tool, provides a complete coverage with structural and formal analysis. It can work on FPGAs of all sizes, and it is highly accurate because of its very proven engines. So with these three tools, your FPGA designs are a lot faster in terms of implementation because your RTL is really signed off from lint and CDC perspective, and your debug cycle time is a lot less. Ascent Lint has about 480 lint rules that really cover all the aspects of your RTL structural issues. And they cover the areas like synthesis subset, clock reset analysis, any flow related issues that you will have with this RTL, any style related issues, coding guidelines, and so on. This is an exhaustive set of rules that we have created based on the industry inputs of different segments. As I mentioned, Ascent Lint is the only linter which is ready to use out of box, requires minimal setup, very, very fast, and provides high value checks. You can configure the rules as per your needs. So we do come up with we have a default rule set that you begin with, but it's very easy to configure the rules within the tool in case you have a custom need and define your own custom policies. Ascent IIV Autoformal provides the formal RTL verification. It provides you with very deep checks which are related to, say, FSM, coverage, and design related, and language related. The FSM is where you may have some your states, like the states of the FSMs may be illegal, or if you have illegal transition between the states, or if you have deadlock between the states. All of this is found using formal techniques. Suggestive, and whatever is found is absolutely surely bound to happen in your RTL. There's no doubt about it. The coverage related issues are things like block. So there is a block of RTL code that cannot be entered ever, that we call dead code. It would be good to know the dead code in advance. If it is advertent, then you need to fix it. And if it is not advertent, then you need to analyze why is there dead code in RTL, which may be taking up area or maybe consuming power. Also, if any signal is declared as a bit, whether it can toggle between 0 and 1. If it's stuck at 0, or if it's stuck at 1, then you would like to know in advance. So all of these checks are performed using formal techniques. As far as design integrity is concerned, there are checks like bus contention. If you have multiple drivers driving a net, or floating bus, or X assignment. Also, there are some language-related checks like range violations. If you have defined a range for a specific variable, and if there is an assignment which goes beyond the range, you would that is found detected using formal techniques, and so on. So AutoFormal provides a very, very exhaustive, deep formal analysis of your RTL and using static techniques. So you don't have to have any test vectors, and you can start these runs before you do simulation. This is an example of an illegal state reachability. Here, as you can see in the RTL fragment, there is A after the state A, next state is B, and the B next state is C, but the next is D. So there is no C that can ever be reached. So that is illegal state declaration. So these kind of things are detected using AutoFormal. One of the key differentiators of AutoFormal is root cause analysis, or what we call smart reporting. It has a map of the dependencies of the violations. So while the violations may be all on different categories, like the middle box here has got different categories, like the pairwise state deadlock, single state deadlock, or X assignment, or constant net. The number of errors that have been found is in the middle box. So overall, there are 2,999 errors that are found in this design, which is about 130K gates block. Usually, the designers are forced to debug the 3,000 violations. But what Ascent IIV AutoFormal tool does is it does categorize the violations in primary and secondary violations. The primary violations are the violation that causes several secondary violations. So if you fixed one primary violation, you have fixed several secondary violations. So overall, you need to only fix 181 violations, and that will take care of your 3,000 violations. So this is one of the big differentiator and debug time saving feature of IIV AutoFormal, and that has led to deployment of this tool in several of the FPGA accounts. The next aspect is the clock domain crossing verification. CDC is a very, very critical problem that is resulting in that can result in chip respins. And the problem is very simple. When you have a transmitting flop operating in a clock domain which is different from the receiving clock domain, then it can cause metastability, what is called metastability. That means at the capture flop, the signal may reach at a time when the clock 2 is not yet active, or it may reach exactly at the same time. So there is a signal loss for at least one cycle, and it will get captured only at the next clock cycle. This signal loss can result in unpredictable behavior of the function and can cause the chip to function badly. So the challenge is it is hard to detect, because if you manually review, there are so many clock domains. As Rama mentioned, now 10 and 20 and 50 clock domains are common in FPGA, and as our polls showed as well, that there are many designs with 30, 40 clock domains. And manual review of this crossing is not practical anymore. So it is hard to detect and diagnose. And with simulation, it is hit and miss. It all depends on the test vectors, and also it takes a long time. And also there is a variety of ways of implementing the crossing, and so that makes it highly challenging. So the impact is chip failure. So how do people take care of this? There is something called synchronization. So you basically add a double flop synchronizer or multi-stage flops as a synchronizer the control that control this data transfer. So Meridian CDC provides the most comprehensive CDC verification, which can look at all the different kinds of synchronization that designs may have and whether they are working properly. So on the top right here, you see incorrect synchronization is detected. There is also glitch scenario. So there could be a glitch that could be happening in the crossing, clock crossing, that is detected in Meridian CDC. Reconvergences. This is also a big problem that has killed some of the chips, where the signals are coming from different clock domains and they reconverge at a different point in the design. And by the way, reconvergence point could be within the block or could also be outside the block. So you may have signals crossing several blocks and reconverging, say, at chip level. So those are also detected using the Meridian CDC product. And lastly, there is also loss of correlation. That is another kind of analysis where here if the signal branch off to different clock paths, clock-driven paths, then the signal may not be correlated at the end of this these two parallel paths. So these are all verified using Meridian CDC. So Meridian CDC has a very comprehensive methodology, which starts with getting your design right. First, using the lint, make sure your RTL is right before you do CDC analysis. Then you do CDC setup. CDC setup means getting the clocks and the resets and the stable values, all of them correctly specified so that you can do the right CDC analysis. If you do not have clock definition ready, then the tool can automatically infer the clocks from RTL. It provides, and if you already have some setup like clocks and resets, then we can perform checks to make sure that they are right. And it provides a good debug for the setup. After you've got your setup right in the middle box, then you do the CDC analysis. That is, making sure your synchronization is correct and your reconvergence is correct, or there is no loss of correlation, or if there is no glitch issues. One of the key features of Meridian CDC is its new debugger. It's called iDebug. It provides a very intuitive and easy to use debugging of the CDC violations. First of all, the CDC and this debug works on a database. So we have a real intent database that stores all the design information and analysis results information, violations, and any other related information in a database, persistent database. So that helps in your productivity, because next time when you rerun, it can start from where you left off. And you can also look at, do custom queries on this database. You can find design objects. You can find specific violation. You can find violation related to specific clock or specific clock domain or a specific block. Also, it provides a very ordered debugging. So it gives a very sequential violation order, so that you can focus on the first one, what you need to focus on first, fix them, then go to the next, fix them, then go to the next. So it is very well ordered debugging. Provides a powerful data selection where you can look at specific views of the design or the specific blocks. It allows for team debug. You can have multiple designers working on the same design for CDC or any application at the same time. So this is just to give an idea of that I debug. Here the violations are shown in a tabular form in the middle, in the spreadsheet kind of form, where you can add column, remove column, you can sort based on columns, and for each of the violation it has a receiving flop and the location, the clock domain it belongs to, and so on. You can click on specific violation and right mouse click, and it gives you further options like viewing the schematic or opening the editor or running a further analysis like formal. So how does real intent flow look like for Altera FPGAs? You start with your RTL. You use tools like Ascent Lint, Ascent IIV, Otterbox, and Meridian CDC to get an improved RTL, which are clean from the lint perspective, from functional integrity perspective, and also from clock domain crossing perspective. And with that, you are much better prepared to go through the Altera tool suite to do your FPGA implementation. Real intent provides a seamless customer experience when you're referencing Altera IPs. If you have Altera IPs or any third-party IP, which the guts is not available for tool analysis, then we do have a way to we provide kind of a custom library, RI library, which can replace your specific library models in your libraries and can still run all the analysis very accurately. We provide these libraries, and there is a seamless reference to this library, so that user doesn't have to change any one of the flow or files when running real intent tools for Altera FPGA. So in summary, as Rama mentioned, Altera provides cutting-edge FPGA development package to create today's systems using Stratix Prime. Getting the RTL right results in faster FPGA design closure and reducing chip spin risks. Using tools like linting, Otterbox, and CDC, you are providing not only faster design closure because your RTL is better, but also reducing the risk of respins because of the metastability issues or reconvergence issues that you are already detected and fixed at RTL. Real intent provides key RTL analysis and sign-off solution like the lint and the IIV and CDC, and it has been proven. We have several FPGA customers who are using our tools in production, in deployment, for getting the design right. And these customers are worldwide, and they span several segments of the customers, including defense, mil-aeros, and the consumer electronics. If you need more information, you can email gran@realintent.com. At this time, I will open the forum for any questions that you may have.
So feel free to use the question box on your control panel and go ahead and submit any questions. Well, while we're waiting for any questions to show up, I'd like to thank Ramesh Dewangan again for his presentation today on how Real Intent tools provide an effective and practical way for doing RTL sign-off for Altera, Stratix, and other FPGA designs. And as well, I'd like to thank again Rama Venkata for presenting on behalf of Altera, now part of Intel. Well, I don't see any questions coming from the audience. So again, I'd like to thank everyone for joining, and we can say our webinar has concluded. Again, if you have any questions, please send them to me, graham@realintent.com. Thank you very much.
Thank you.
Thanks. Bye.